Hi, today we will discuss safety provisions as provided by ECI. Structures and structural members must always be designed to carry some reserve load above what is expected under normal use. So take note there should be a reserve load for your design. And such reserve capacity is provided to account for a variety of factors, which may be grouped into two general categories, that is, factors relating to overload and factors relating to understrength. So take note, we have overload and understrength. Overloads may arise from changing the use for which the structure was designed, from underestimation of the effects of loads by oversimplifications in calculation procedures, and from effects of construction sequence and methods. First, normally we underestimate the effects of loads because we oversimplify it. Also, during construction, we normally assign some loading, but some of the the construction workers will just suddenly put some loading that is not intended during the design. Also, for the understand, this may result from adverse variation in material strength, workmanship, dimensions, control, and degree of supervision. During the manufacturing of the material, especially for the structural steel, there will be some variations, but at least they can control that one. In terms of the concrete, that's the most difficult part of reinforced concrete because it's not always easy to maintain the material strength of the concrete mix. Because of that, the safety provisions of the ECI actually, the purpose of the safety provision is to limit the probability of failure and yet permit economical structures. Obviously, if cause is no object, it is easy to design a structure whose probability of failure is nil. But that's not usually what happens because normally we have a limited budget, so we need to design the structure whose probability of failure is low, not necessarily nil. To arrive properly at a suitable degree of safety, the relative importance of various items must be established. Some of these items are, first, the seriousness of a failure, either to humans or goods. Two, reliability of workmanship and inspection. Third, expectation of overload and to what magnitude. Four, importance of the member in the structure. And fifth, chance of warning prior to a failure. By assigning percentages to these five items and evaluating the circumstances for any given situation, proper values for overload factors, we call it capital U, and strength reduction factors pi can be established. So in the next topics, we will be discussing these overload factors U and the strength reduction factor pi. For the basic design relationships, especially for beams with loads and the load effects, look at the beam with loads and load effects on the left-hand side of the slides. A beam that supports its own weight W plus some applied loads P1, P2, and P3. These loads cause bending moments as shown on figure B. The moment diagram is independent of the composition or shape of the beam. The bending effect or the bending moment is referred to as the load effect for this particular case. Other load effects include, of course, shear force, axial force, torque, deflection, and vibration. Here, the figure shows the flexural stresses acting on a beam cross-section. That is, if we have to cut the section or the beam, as you can remember in your structural theory, we normally use cutting. If we cut a certain section of the member, then we will see the internal forces. In this particular diagram, you will see the compressive and the tensile stress blocks, which can be replaced by the forces capital C and capital T separated by a distance JD. The resulting cofold is called the internal resisting moment. I hope you still remember that in your structural theory. Here, this is very important because we will be using these forces, the compressive force C and tensile force T, to design our structural members. This internal resisting moment when the cross-section fails is referred to the moment strength or the moment resistance. So by now you have the new word, the moment strength or the moment resistance. The word strength also can be used to describe the shear strength or the axial load strength. First, the beam in the previous slide will support the loads safely if, take note, at every section the resistance or strength of the member exceeds the effects of the load. So this is stated in very simple way. Resistances should be greater than or equal to the load effects. To allow for the possibility that the resistances will be less than computed or the load effects larger than computed, the following are introduced. The one that I told you earlier, we have the strength reduction factor pi, which is usually less than 1, and load factors alpha greater than 1. So to apply these factors, we need to multiply the nominal resistance strength, that is R sub n, by a certain factor pi, the strength reduction factor. So as you can see in equation 2, the resistance is actually equal to the nominal resistance R sub n with the subscript n because this is nominal times the strength reduction factor pi. Uh, and it should be always greater than or equal to the load effects. Here the load effect should be the the different loads multiplied by the load factors alpha. So we have the loading is 1 to be multiplied by alpha 1 plus loading is 2 to be multiplied by alpha 2. So this is just a very basic equation in which we will be using in our design. So take note that the basic equation is that the resistance or the strength should always be greater than the load effects, or it can be further written in terms of the strength reduction factor pi and the load factors alpha. That is pi Rn should always be greater than or equal to alpha 1 is 1 plus alpha 2 is 2 plus other loads. If you have to write that in terms of the moments, so instead of using R, we can use the moment M. So pi sub M, M sub N, meaning pi is the strength reduction factor for the moment, and mn, again, if you have a subscript n, this means nominal. The nominal moment strength mn should always be greater than or equal to alpha d, that is for the dead load, times the moment due to the dead load plus alpha l, that is live load, times the moment due to live load plus other uh, loadings. So here mn is the nominal strength, nominal moment strength. The word nominal implies that this strength is a computed value based on the specified concrete and steel strengths and the dimensions shown on the drawing. Of course, other equations can be similarly written for the shear and the axial force as shown in equations 4 and equation 5. In ACI, the symbol capital U is used to refer to the combination below and is referred to as the factored loads. So going back to equations 3, 4, 5, looking at the right-hand side of the equation, this can be written as capital U. That is alpha D, capital D, plus alpha L, capital L, plus other loading. So the symbols M sub U, V sub U, T sub U, and so on is referred to as the factored load effects calculated from the factored loads. So with the subscript U, this means factored load effects. So for example, for the moment that is M sub U, this is the factored load or the factored bending moment, M sub U, which is equal to alpha D MD plus alpha L ML. And thus pi sub m, m sub n is greater than or equal to alpha d md plus alpha l ml plus other loading. Or this can be simplified in this way. Pi sub m sub n is greater than or equal to mu. So instead of writing the longer terms in equation 8 on the right hand side, you can just say it's m sub u. So the basic equation for strength design method is that the resistances should be greater than or equal to the load effects, or the strength provided should always be greater than the required strength, or the design strength should always be greater than the required strength. This design strength is normally the nominal strength times the strength reduction factor pi. Should be greater than or equal to the ultimate load, capital U. Or to shorten it, the symbol should be pi, r sub n should be greater than or equal to U. For members subjected to moment, shear, and axial load, you can write it this way. Pi mn greater than or equal to mu, or pi vn greater than or equal to vu, and pi pn greater than or equal to pu. In the next topic, we will discuss the different values of pi on how to determine it, and also the different values for the factor loads for the capital U. Okay, so thank you for listening.